DeepSeek just released something that completely changes how AI reads documents. And honestly, the OCR world is still figuring out what just happened. We're talking about DeepSeek OCR 2, a 3 billion parameter model that hit 91.09% on the toughest document test while using only 256 to 1120 visual tokens per page. And the crazy part is, they swapped out their image reader with a small language model that actually thinks about what it's looking at. Let me explain why this matters and why every company processing documents should be paying attention right now. Alright, so DeepSeek OCR 2 dropped on 27th of January 2026. And the first thing everyone noticed was the benchmark score, 91.09% overall on OmniDocBench v1.5. That's a 3.73% jump over the previous version. And here is the thing, most OCR models improve by maybe half a percent when they get updated. DeepSeek posts nearly 4 full points, but the real breakthrough shows up in a number called reading order edit distance. The first version sat at 0.085. Versions 2 slashed that down to 0.057. That number directly tells you how well the model understands the logical flow of a document. Tables, footnotes, multi-column layouts, all the stuff that confuses normal OCR tools. DeepSeek OCR 2 reads them in the right order now. And when they put it next to Gemini 2.5 Pro using the same visual token budget, around 1120 tokens per page, DeepSeek OCR 2's document parsing edit distance hit 0.100. Gemini 2.5 Pro came in at 0.115. So DeepSeek actually beat a closed source model from Google while staying completely open source. That changed the conversation immediately because most companies assumed you needed massive private systems to get top level document understanding. DeepSeek just proved you don't. Now, the numbers behind this jump are wild. DeepSeek revealed that when processing online user log images, the repetition rate dropped from 6.25% down to 4.17%. In PDF data production work, it fell from 3.69% to 2.88%. Trainer outputs mean better training data for language models later. This isn't just about accuracy, it's about usable data at a huge size. Here is where it gets interesting. The core upgrade sits inside something called Deep Encoder v2. The first version of DeepSeek OCR used a CLIP-based visual encoder. CLIP is great at pulling features from images, but it doesn't reason. It just matches patterns. Version 2 swapped that out for Qwen205B, a small language model changed into a vision encoder. And that shift changed everything because language models understand ordering, logic, and how things connect. So instead of just seeing patches of pixels, the encoder now thinks about what those pixels mean and how they connect. The technical term for this is visual causal flow. Traditional OCR systems scan documents in a stiff raster pattern, top left to bottom right, line by line. That works fine for simple text blocks. But when you throw in a newspaper with ads, slideboards, and columns, or a science paper with math and graphs, that fixed scan destroys the meaning structure. You end up reading a table header, then jumping to a random paragraph in the middle, then back to a footnote. The model loses what's happening. The DeepCoder V2 solves this by using two attention systems at the same time. Visual tokens get two-way attention, meaning they can see the full image like a normal vision transformer. But then there is a second layer called Causal Flow tokens. These use one-way causal attention, exactly like a language model decoder. Each flow token can look at all the visual tokens and the flow tokens that came before it. This creates a step-by-step reordering process. The encoder figures out the logical reading order before it even sends anything to the decoder. So by the time the language model gets the tokens, they are already organized in a way that makes sense. Header first, then body paragraphs, then table data, then footnotes, the same way a human would read it. And to keep everything working well, they still use the same tokenizer from the first version. images get squeezed through a 16 times shrinking process. A 1024 by 1024 pixel image that would normally make 4096 tokens shrinks down to just 256 tokens after squeezing. Then the model crops the image into local views if needed, each with 144 query pieces. Total visual token count ranges from 256 up to 1120 depending on the document size. That matches what Gemini 2.5 Pro uses and stays way below what older model needed. GOAT OCR 2.0 needed 256 tokens per page at a minimum. Minor U 2.0 burned through 6000 tokens on average. DeepSeek OCR 2 does more with less. Another piece that makes this work is the decoder. DeepSeek kept the same 3 billion parameter mixture of experts language model from version 1. It turns on around 570 million parameters per token. The decoder doesn't need to change because the encoder already handed it a clean, meaningfully ordered token order. The decoder just reads and makes output. No more fighting with jumbled layouts or guessing the structure. The thinking happened earlier in the process. Now, let's talk about what this actually does in the real world. The training process is where things get serious. DeepSeek collected 30 million PDF pages covering around 100 languages, with Chinese and English making up 25 million pages. The training data spans 9 document types: academic papers, financial reports, textbooks, newspapers, handwritten notes, and other. Beyond document OCR, the training added what they call OCR 2.0 data: 10 million made-up charts, 5 million chemical formulas, and 1 million geometric figures. The model also got 20% general vision data for tasks like image captioning and object spotting, plus 10% text-only data to keep language ability strong. The variety lets it read science papers, textbooks, and technical documents without breaking its flow. For math-heavy content, the model handles complex formulas, chemical structures in smiles format, and geometric figures. The training process used pipeline working across 160 NVIDIA A140G GPUs. That's 20 nodes with 8 GPUs each. The vision encoder divided between 2 pipeline stages and a language model split across 2 others. This setup processes around 70 billion tokens per day for multimodal data. And then there is the squeezing ability. On the first test, DeepSeek OCR 2 hit 97% accuracy at 10 times squeezing. That means you can shrink visual context by a factor of 10 and still get nearly perfect text pulling. At 20 times squeezing, accuracy drops to around 60%, which is still usable for certain work like historical long context squeezing or memory systems in language models. From a setup standpoint, you have got 3 main choices. You can use the Transformers library directly from HuggingFace, run it through vLLM for faster work, or use Unsloth for better fine-tuning. When using Unsloth for fine-tuning on custom datasets, users have reported accuracy improvements of 57 to 86% reduction in character error rate. That's massive for companies dealing with special document types or industry-specific layouts. The model supports 2 prompt modes. Document mode uses the grounding tag and keeps layout structure, tables, and formatting. Free OCR mode just pulls text without layout keeping. Base mode runs on GPUs with 8 to 10 GB of VRAM. If you want the full dynamic tiling mode for high quality images, you will need 40 GB, which means an A100 or similar. Hardware-wise, the speed scales clearly. The first version of DeepSeek OCR could process around 200,000 pages per day on a single A140G GPU. In production settings, a single A100 GPU can handle roughly 200,000 pages daily, while scaling to a full cluster of 20 servers with 8 GPUs each pushes throughput to around 33 million pages per day. If you are running on a regular hardware like RTX 4090, you can still handle medium workloads in base mode. CPU-only setups work but are much slower. For company workloads, you group pages together to get the most out of GPU use. A typical academic paper with diagrams takes around 0.4 seconds per page. A simple invoice processes in 0.1 seconds. That speed combined with the low token count makes it practical for large-scale document digitizing projects. Now, the bigger picture here is what DeepSeek calls native multimodality. They mentioned at the end of the technical paper that the deep encoder V2 proves the idea of using a language model as a visual encoder. And this isn't just an OCR upgrade, it's a setup toward a unified encoder that can handle text, images, and audio with the same building blocks. You just swipe out the query pieces for different types. That means in the future, the same encoder could squeeze speech features, recognize visual content, and process text all within the same parameter space. Everything becomes tokens. Everything becomes thought through with cause and effect. That's where we will wrap it up. One thing I'm curious about now is how this building style grows to other visual thinking tasks beyond documents. DeepSeek mentioned they will keep looking at general multimodal intelligence. If the causal flow approach works this well on text-heavy layouts, imagine what happens when you apply it to video, 3D scenes, or real-time visual understanding. Drop your thoughts below. Make sure you are subscribed, hit the like button, and I will see you in the next one.